Close your eyes and let your body sink deeper into comfort. Feel the weight of the day dissolving, each breath carrying away tension, each moment bringing you closer to peaceful rest. Tonight, we're going on a gentle journey through time, exploring the most profound discoveries that shaped the human experience. Let these stories wash over you like waves on a shore, their rhythm soothing, their significance timeless. There's no need to remember every detail. Just let the words flow through your consciousness like a river, carrying you toward deep, restorative sleep. As we explore these 77 moments when humanity glimpsed truth, allow yourself to drift, to float, to surrender to the embrace of rest. Your breathing is slowing, your mind is quieting, and the discoveries we'll encounter together will unfold like stars appearing in a darkening sky, beautiful, distant, and perfectly arranged to guide you into slumber. Perhaps no single discovery transformed human existence more fundamentally than our ancestors' ability to control fire. Somewhere between 1 million and 400,000 years ago, early humans learned to harness this elemental force that had previously existed only as a wild phenomenon, sparked by lightning, erupting from volcanic activity, burning through forests in terrifying waves. The exact moment when someone first captured flame and kept it alive remains lost to prehistory, but archaeological evidence from sites across Africa and Asia tells us that Homo erectus was using fire systematically by at least 400,000 years ago, perhaps much earlier. The mastery of fire represented far more than simple warmth on cold nights. It fundamentally altered human biology and society in ways that still echo through our modern world. Cooking food made nutrients more bioavailable and easier to digest, allowing our ancestors to extract more energy from the same amount of food. This nutritional revolution may have supported the development of our large, energy-hungry brains. The digestive systems of humans gradually adapted, becoming smaller than those of our ancestors because cooked food required less processing. Fire extended the day, creating a safe circle of light where stories could be shared, tools could be crafted, and social bonds could strengthen after darkness fell. It provided protection from predators, whose eyes gleamed at the edge of the firelight, but who dared not enter the sphere of flame. Fire enabled humans to expand into colder climates, carrying warmth with them as they migrated across continents and into regions that would otherwise have been inhospitable. It allowed for the creation of more sophisticated tools through heat treatment of stone and, eventually, the smelting of metals. Clay hardened in flames became pottery, capable of storing food and water. The controlled burn transformed landscapes, clearing forests for agriculture and managing ecosystems. In the dancing flames, humans found not just a tool, but a companion, a teacher, and a pathway to civilization itself. The hearth became the center of human life, and though we now command fire through switches and buttons, that ancient relationship remains embedded in our psyche. We still gather around warmth, still find comfort in the flicker of flame, still feel something primal stir when we watch fire dance against the darkness. Around 5,500 years ago, in the ancient region of Mesopotamia, someone made a leap of imagination that seems almost impossibly simple in retrospect. They took a circular disc, bored a hole through its center, and mounted it on an axle that allowed it to rotate freely. This was the wheel, and it stands as one of humanity's most ingenious inventions, so fundamental to modern life that we can scarcely imagine existence without it. Yet the wheel's journey through history reveals something fascinating about innovation itself. The earliest wheels weren't designed for transportation at all. Archaeological evidence suggests they first appeared as potter's wheels, spinning discs that allowed artisans to craft symmetrical vessels with unprecedented ease and efficiency. The connection between this rotating platform and the possibility of wheeled vehicles required another conceptual leap, understanding that a rotating disc could not just shape clay, but could carry weight across distance. The first wheeled vehicles appeared in several locations almost simultaneously around 3,200 years before the Common Era, suggesting that once the idea emerged, it spread rapidly through trading networks. These early wagons and carts were crude affairs, solid wooden wheels attached to fixed axles, creaking and groaning as they rolled, sometimes pulled by oxen or donkeys. But they revolutionized transportation, allowing humans to move heavier loads farther than ever before. A person can carry perhaps 50 pounds comfortably for a day's journey. A wheeled cart pulled by an ox could transport hundreds of pounds, then thousands as the technology improved. The wheel's influence rippled through society in unexpected ways. It enabled trade on a scale previously impossible, connecting distant communities and facilitating the exchange of goods, ideas, and innovations. It transformed warfare, giving rise to chariots that dominated ancient battlefields. It revolutionized agriculture, allowing for plows and harvesting equipment that dramatically increased food production. Over millennia, the simple wheel evolved into countless variations: the pulley, the gear, the water wheel, the turbine. The Industrial Revolution turned on wheels of unprecedented size and precision. Today, wheels remain everywhere, in our vehicles, our machinery, even in the digital realm where we still speak of gears and wheels turning in metaphorical ways. That ancient Mesopotamian innovation, born from clay and imagination, continues to carry human civilization forward 10,000 years ago. Perhaps a bit more, humans made a choice that would fundamentally and irreversibly alter our species' relationship with the natural world. Instead of following herds and gathering whatever plants grew wild, groups of people in several locations around the globe began deliberately planting seeds, nurturing crops, and domesticating animals. This transition from nomadic hunting and gathering to settled agriculture unfolded over centuries, a gradual shift rather than a sudden revolution, yet its consequences were revolutionary indeed. The Fertile Crescent, that arc of land stretching from modern-day Egypt through the Levant and into Mesopotamia, witnessed some of the earliest agricultural experiments. Wheat and barley, legumes and flax, became the foundation crops. In East Asia, rice cultivation began along river valleys. In Mesoamerica, maize, beans, and squash formed an agricultural triad. In the highlands of South America, potatoes and quinoa sustained emerging civilizations. Each region developed agriculture independently, selecting and improving local plants through patient observation and experimentation spanning countless generations. Agriculture demanded a new way of living. Nomadic bands settled into permanent villages, building structures meant to last, storing surplus grain in vessels and granaries, marking time by seasons of planting and harvest rather than the movements of game. Population densities increased dramatically because farmland could support far more people per square mile than hunting territories. This population growth created both opportunities and challenges. More hands to work the fields, but also more mouths to feed, more complex social structures to organize, more conflicts to resolve. The agricultural revolution made civilization possible in the form we recognize it. Surplus food freed some individuals from constant food production, allowing specialization of labor. Some became craftspeople, others priests, others administrators and warriors. Social hierarchies emerged, along with concepts of property ownership and inheritance. Writing systems developed to track harvests and taxes. Cities rose from agricultural surplus, their marketplaces bustling with trade. Yet agriculture also brought new vulnerabilities. Crop failures could devastate entire populations. Epidemic diseases flourished in densely packed settlements, and the hard labor of farming wore down bodies in ways that hunting and gathering had not. The domestication of animals paralleled plant cultivation, transforming wolves into dogs, wild aurochs into cattle, wild boars into pigs. Animals provided not just meat but milk, wool, leather, and labor, plowing fields, pulling carts, carrying riders into battle. The relationship between humans and these domesticated species became deeply symbiotic, each shaping the evolution of the other. Agriculture was neither purely beneficial nor entirely detrimental. It was transformative, setting humanity on a path from which there could be no turning back, toward increasing complexity, technological sophistication, and interconnection. Imagine a world where knowledge dies with each generation, where the accumulated wisdom of a lifetime vanishes when its holder does, where messages cannot travel farther than a messenger's memory can carry them. This was human existence for hundreds of thousands of years. Then, around 5,000 years ago, something extraordinary happened. Humans began to encode language into permanent visual symbols. Writing emerged, and with it came the ability to transcend the limitations of memory and mortality. The earliest writing systems appeared in ancient Mesopotamia, where Sumerian scribes pressed reed styluses into soft clay tablets, creating wedge-shaped marks we now call cuneiform. These early texts were primarily administrative. Records of goods, tallies of grain and livestock, receipts for transactions. But the technology of writing, once invented, proved capable of capturing far more than mere accounting. Epic poems like Gilgamesh, legal codes like Hammurabi's, letters between lovers, prayers to gods, astronomical observations, medical treatments, all became permanent, transferable, preservable across generations. Around the same time, perhaps slightly earlier, ancient Egypt developed hieroglyphic writing, a complex system combining logographic and alphabetic elements, painting and carving their symbols on temple walls, papyrus scrolls, and tomb inscriptions. In the Indus Valley, another script emerged, still undeciphered, its secrets locked in ancient seals and tablets. Ancient China developed its distinctive character-based writing system, ancestor to modern Chinese script, beginning around 3,500 years ago. Mesoamerican cultures created their own writing systems independently, the Maya producing a fully developed script capable of expressing any thought in their spoken language. The invention of alphabetic writing, where symbols represent individual sounds rather than whole words or concepts, represented another revolutionary step. The Phoenician alphabet, developed around 3,300 years ago, became the ancestor of most modern alphabetic systems: Greek, Latin, Cyrillic, Arabic, Hebrew. An alphabet required learning only a few dozen symbols rather than thousands of characters, making literacy more accessible, though still limited to a small, educated class for most of history. Writing transformed human civilization in profound ways. It enabled the accumulation and refinement of knowledge across generations. A scholar could read texts written centuries before, build upon earlier insights, and record new discoveries for future generations. Legal systems could codify laws precisely and consistently. Religious texts could preserve sacred teachings. Historical events could be recorded for posterity. Scientific observations could be documented and compared. Literature could explore the depths of human experience and imagination. Education became formalized, with knowledge transmitted through texts as well as personal instruction. The printing press, invented by Johannes Gutenberg around 1455, democratized access to written knowledge, but writing itself was the foundational innovation. Digital communication has transformed how we write and share text, but we're still using this 5,000-year-old technology, encoding our thoughts into symbols that persist beyond the moment of their creation. Every book, every text message, every social media post, every scientific paper is a descendant of those first clay tablets pressed in ancient Mesopotamia. Numbers surround us so completely that we rarely pause to consider their abstraction, their essential strangeness. A 3 doesn't exist in the physical world. We can see 3 apples, 3 people, 3 stars, but threeness itself is a concept, an abstraction our minds create. The development of mathematical thinking represents one of humanity's greatest intellectual achievements, a framework for understanding patterns, quantities, relationships, and change that has proven astonishingly powerful at describing reality. The earliest mathematics emerged from practical needs. Ancient peoples developed number systems for counting livestock, measuring grain, tracking days and seasons, dividing land. Evidence of mathematical thinking dates back at least 20,000 years. The Ishango bone from Africa bears tally marks that may represent a lunar calendar or menstrual cycle tracking. Ancient Babylonians developed sophisticated arithmetic and algebra, solving quadratic equations and working with a base 60 number system that gave us 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. Egyptian mathematics, preserved in papyri like the Rhine mathematical papyrus, shows calculations of areas and volumes, solutions to practical problems of construction and commerce. The ancient Egyptians used fractions and developed geometric principles that allowed them to build the pyramids with astonishing precision. They surveyed land annually after Nile floods, recalculating boundaries with mathematical accuracy that settled disputes and ensured fair taxation. But it was ancient Greece where mathematics truly blossomed as abstract intellectual pursuit rather than just practical tool. Pythagoras and his followers explored the mystical properties of numbers and discovered the famous theorem relating the sides of right triangles. Euclid systematized geometry in his Elements, a work that remained the standard geometry textbook for over 2,000 years. Archimedes calculated areas and volumes with methods that anticipated integral calculus. Eratosthenes measured Earth's circumference with impressive accuracy. Greek mathematicians proved that certain numbers like the square root of 2 are irrational, that certain geometric problems cannot be solved with compass and straightedge, that prime numbers are infinite. India gave the world the concept of zero as a number rather than just a placeholder, a profound innovation that took centuries to spread westward. Indian mathematicians developed early algebra, worked with negative numbers, and understood basic trigonometry. Islamic scholars preserved and extended Greek mathematical knowledge during Europe's medieval period, developing algebra. The word itself comes from Arabic al-jabr, refining trigonometry, and inventing algorithms, named after the mathematician al-Khwarizmi. The Renaissance and Enlightenment saw mathematical progress accelerate. Descartes merged algebra and geometry into analytic geometry. Newton and Leibniz independently invented calculus, providing mathematics with tools to analyze motion, change, and continuous variation. Probability theory emerged from questions about gambling, becoming essential for statistics and scientific inference. Non-Euclidean geometries showed that Euclid's parallel postulate wasn't necessary, revealing that multiple consistent geometries were possible. Modern mathematics has become increasingly abstract and specialized, exploring structures, patterns, and relationships for their own sake. Yet practical applications continually emerge from seemingly pure theory. Number theory, long considered the most useless branch of mathematics, now underpins modern cryptography. Topology, abstract algebra, differential geometry, all find applications in physics, computer science, engineering, economics, biology. Mathematics remains humanity's most powerful tool for understanding the universe's deep structure, from quantum mechanics to general relativity, from population dynamics to financial markets. It is simultaneously invention and discovery, a language we created that somehow perfectly describes realities we didn't create. Look up on a clear night, away from city lights, and you'll see what every human being for hundreds of thousands of years has seen: the vast dome of stars wheeling overhead, the moon cycling through its phases, planets wandering among fixed constellations. Ancient peoples watched these skies with attention we can barely imagine, marking patterns, noting cycles, constructing calendars, and weaving the heavens into mythology and religion. But alongside myth and wonder, they also practiced careful, systematic observation, astronomy, humanity's oldest science. The ancient Babylonians were meticulous astronomical record keepers, tracking planetary positions and lunar cycles over centuries, discovering the Saros cycle that allows prediction of eclipses, developing sophisticated mathematical models of celestial motions. Their astronomical diaries, recorded on clay tablets, represent some of humanity's first scientific data collection. Ancient Egyptian astronomy was closely tied to timekeeping and agriculture. The heliacal rising of Sirius signaled the annual Nile flood, and they developed a calendar of 365 days. Ancient China maintained detailed astronomical records for over 3,000 years, noting comets, novae, and meteor showers. Chinese astronomers developed star catalogs, understood that the sun moves through the zodiac, and built elaborate astronomical instruments. Mesoamerican cultures, particularly the Maya, developed incredibly accurate calendars based on detailed astronomical observations, tracking Venus cycles and predicting eclipses without telescopes or modern instruments. Greek astronomy became more theoretical, attempting to explain celestial phenomena through geometric models. Hipparchus cataloged over 800 stars, discovered the precession of the equinoxes, and developed trigonometry for astronomical calculations. Ptolemy's geocentric model, placing Earth at the universe's center with planets moving in epicycles, explained celestial motions with impressive accuracy and dominated Western astronomy for over 1,000 years. Islamic astronomers preserved and extended Greek astronomical knowledge, building observatories, refining star catalogs, and improving astronomical instruments. Al-Sufi's book of fixed stars described star magnitudes and positions. Al-Biruni discussed the possibility of Earth's rotation. Persian astronomers at the Maraga Observatory developed new planetary models that would later influence Copernicus. The astronomical revolution that began with Copernicus placing the Sun at the center of the solar system transformed humanity's cosmic perspective. Tycho Brahe made unprecedentedly accurate naked-eye observations of planetary positions. Johannes Kepler discovered that planets move in elliptical orbits following mathematical laws, revealing divine order through natural law rather than complex epicycles. Galileo's telescope revealed mountains on the Moon, Jupiter's satellites, Venus's phases, countless stars invisible to naked eyes, direct evidence that the cosmos was more complex and vast than previously imagined. Newton's law of universal gravitation showed that the same force pulling apples to the ground also keeps planets in orbit, unifying terrestrial and celestial physics. Astronomy became less about mapping positions and more about understanding physical processes. Spectroscopy, developed in the 19th century, allowed astronomers to determine stellar composition, temperature, and motion without ever visiting stars. The cosmic distance scale gradually expanded. Stars are suns at enormous distances. Galaxies are vast systems of stars. The universe itself is expanding. 20th and 21st century astronomy has revealed an almost incomprehensibly large and ancient universe. 13.8 billion years old, 93 billion light-years in diameter, the observable portion, containing perhaps 2 trillion galaxies, each with hundreds of billions of stars. We've detected exoplanets, observed black holes, measured cosmic microwave background radiation, found evidence for dark matter and dark energy. Yet at its heart, modern astronomy continues the same practice that ancient Babylonians began: careful observation of the sky, patient record-keeping, and the search for patterns and meaning in celestial phenomena. Science, as we understand it today, isn't merely accumulated facts about the natural world. It's a specific approach to investigating reality, a systematic method for asking questions, gathering evidence, testing hypotheses, and building reliable knowledge about how things work. The development of the scientific method represents a profound shift in human thinking, from relying on authority, tradition, and speculation to demanding empirical evidence and logical reasoning. Elements of scientific thinking appeared in various ancient cultures. Greek philosophers like Aristotle emphasized observation and classification, though they often preferred logical deduction to experimentation. Islamic scholars like Al-Hazen studied optics through careful experiments, developing principles we'd recognize as scientific. Medieval European scholars began emphasizing empirical observation alongside theological reasoning. But the scientific revolution of the 16th and 17th centuries crystallized these elements into something recognizable as modern science. Francis Bacon championed inductive reasoning, gathering many observations to derive general principles, and emphasized systematic experimentation. René Descartes advocated mathematical reasoning and methodical doubt, questioning everything except what could be proven rationally. Galileo combined observation, experiment, and mathematical description, dropping objects to test theories about falling bodies, using telescopes to gather astronomical evidence, advocating for heliocentrism against entrenched authority. The scientific method, as it emerged, involved several key steps. First, careful observation of natural phenomena, noting patterns and anomalies. Second, formulating questions or identifying problems to solve. Third, researching existing knowledge about the subject. Fourth, forming hypotheses, testable explanations for observations. Fifth, designing and conducting experiments to test hypotheses, controlling variables and measuring outcomes precisely. Sixth, analyzing data to determine whether evidence supports or contradicts hypotheses. Seventh, drawing conclusions and communicating results to others for verification and critique. Eighth, repeating experiments, refining hypotheses, and gradually building more comprehensive theories. Critical to this method is its self-correcting nature. Scientific knowledge is always provisional, always open to revision in light of new evidence. No authority is beyond question, no theory beyond testing. What matters isn't who proposes an idea, but whether evidence supports it. Reproducibility is essential. Other researchers must be able to repeat experiments and get similar results, ensuring findings aren't flukes or errors. Peer review became standard practice. Before publication, research must withstand scrutiny from other experts who check methodology, analysis, and conclusions. This process isn't perfect. Biases exist, mistakes happen, frauds occasionally occur, but it creates a collective filter that catches many errors and gradually converges on accurate understanding. The scientific method has limitations. It cannot answer ethical questions or determine values. Science can tell us what is, but not what should be. It works best with phenomena that can be observed, measured, and tested repeatedly. Some important questions fall outside its scope, and some phenomena are so complex that simple controlled experiments are impossible. Scientists themselves are human, susceptible to bias, ambition, and error. Yet despite these limitations, the scientific method has proven extraordinarily successful at generating reliable knowledge about the natural world. From understanding disease mechanisms to predicting weather patterns, from developing new materials to exploring distant planets, the scientific method has enabled an explosion of knowledge unprecedented in human history. Every technology we use, every medical treatment we receive, every environmental policy we enact rests on foundations of knowledge built through systematic scientific investigation. The method itself continues evolving. Computational science, data science, citizen science, interdisciplinary collaboration all expand how we pursue scientific understanding. But the core principles remain. Observe carefully, question rigorously, test systematically, revise honestly. Before the mid-15th century, books in Europe were rare and precious objects, laboriously copied by hand, page by page, typically by monks working in monastery scriptoriums. A single copy of the Bible might take a year to produce. Books were expensive enough that they were often chained to shelves, too valuable to risk theft. Learning was largely limited to those with access to these scarce texts: clergy, nobility, scholars at universities. Knowledge circulated slowly, constrained by the bottleneck of manual copying. Johannes Gutenberg changed everything. Around 1455 in Mainz, Germany, he perfected a system of movable type. Individual metal letters that could be arranged into words and pages, printed, then rearranged for the next page. The concept of movable type wasn't entirely new. China had been using wooden movable type for centuries, but Gutenberg's innovation combined several key elements into a practical system. He developed an alloy of lead, tin, and antimony that could be cast into durable, uniform letters. He adapted the wine press into a printing press capable of applying even pressure. He created oil-based ink that adhered to metal type better than water-based ink. The result was revolutionary. A press could produce hundreds of copies of a page in the time it took a scribe to copy it once. Books became less expensive, more available. Gutenberg's first major work was the Gutenberg Bible, printed around 1454. About 49 copies survive, testimony to their superior quality. Gutenberg didn't just mechanize book production, he maintained high aesthetic standards. The printing press spread rapidly across Europe. By 1490, printing establishments existed in every major European city, producing thousands of titles. The Renaissance and Reformation both gained momentum from the ability to disseminate ideas widely. Martin Luther's 95 Theses and subsequent writings spread throughout Germany in weeks rather than decades, fueling religious upheaval. Scientific works could be distributed broadly, allowing researchers across Europe to build on each other's work rather than rediscovering the same findings independently. Printing standardized texts, reducing copying errors that had multiplied through generations of hand transcription. It standardized spelling and grammar within languages. It preserved knowledge more reliably. Many copies scattered across multiple locations rather than single manuscripts vulnerable to fire, decay, or destruction. It enabled new forms of publication. Newspapers brought current events to masses, enabling more informed public discourse. Pamphlets and broadsheets became tools for political organizing and social movements. The printing press democratized learning. As books became affordable, literacy rates began rising. Education expanded beyond clergy and nobility. Public libraries emerged. The idea that knowledge should be accessible to all gained traction, eventually becoming a foundational principle of democratic societies. Scientific societies and journals emerged, creating communities of researchers sharing findings and critiquing each other's work. Printing's impact extended to art and illustration. Dürer's engravings could be reproduced and distributed. Maps became standardized and widely available, enabling more accurate navigation and geographic understanding. Musical notation could be printed, standardizing and preserving compositions. Ultimately, printing was about more than technology. It was about accelerating the flow of information, amplifying the reach of ideas, and enabling the rapid accumulation and dissemination of knowledge that characterizes modernity. For most of human history, the geocentric model of the universe seemed obviously correct. Earth feels stationary beneath our feet. The sun appears to rise in the east and set in the west, clearly moving around Earth. The moon and planets trace paths across the sky. The stars will overhead in their nightly dance. Everything seemed to circle Earth, and this view aligned with religious teachings that placed humanity at creation's center, spiritually and physically. But some ancient thinkers questioned this view. Aristarchus of Samos proposed around 250 years before the Common Era that Earth and other planets orbit the Sun, though his ideas didn't gain acceptance. The dominant view remained Ptolemy's geocentric model, which explained planetary motions through complex systems of epicycles. Circles within circles that predicted planetary positions with reasonable accuracy. Nicholas Copernicus revived heliocentrism in the 16th century. Working in Poland, he spent decades developing a mathematical model that placed the Sun at the solar system's center, with Earth and other planets orbiting it. His book De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, published just before his death in 1543, presented this model with detailed calculations. Copernicus's system was still imperfect. He retained circular orbits and some epicycles because he didn't yet know planets move in ellipses, but it was fundamentally correct about the Sun's central position. The Copernican model faced significant resistance. It contradicted religious teaching and common sense. If Earth moved, why didn't we feel it? Why didn't objects fly off its surface? Why didn't the atmosphere get left behind? These were reasonable objections given knowledge at the time. The heliocentric model also lacked direct observational proof. Stars showed no parallax, apparent shift in position as Earth moved through its orbit, because they were far more distant than anyone imagined. Evidence gradually accumulated. Tycho Brahe made incredibly precise observations of planetary positions using naked eye instruments. His assistant Johannes Kepler analyzed this data and discovered that planets orbit in ellipses, not circles, and follow mathematical laws that describe their speeds at different points in their orbits. Kepler's laws simplified the heliocentric model, eliminating the need for epicycles and providing predictive accuracy superior to Ptolemy's system. Galileo's telescope provided visual evidence. He observed phases of Venus, which could only occur if Venus orbited the Sun. He saw moons orbiting Jupiter, proving that not everything circles Earth. He found mountains on the Moon and spots on the Sun, showing celestial bodies weren't perfect, unchanging spheres as Aristotelian philosophy claimed. His observations supported Copernicanism so strongly that the Catholic Church, feeling its authority challenged, eventually placed him under house arrest. Isaac Newton explained why heliocentrism worked. His law of universal gravitation showed that the same force pulling apples to Earth also keeps planets in orbit around the Sun. More massive objects dominate gravitationally, so the Sun's enormous mass naturally makes it the orbital center. Newton's laws of motion explained why we don't feel Earth's rotation. Everything on Earth moves together at the same speed, so there's no relative motion to feel. Stellar parallax was finally detected in 1838, providing direct proof of Earth's orbital motion. As measurement precision improved, the sun-centered model proved increasingly accurate. Eventually, we realized the Sun itself isn't the universe's center. It's one star among hundreds of billions in the Milky Way galaxy, which is itself one galaxy among trillions in the observable universe. There's no cosmic center, no privileged position. Copernicus didn't just rearrange the solar system. He initiated a profound shift in perspective, the realization that humans occupy no special place in the physical universe, that we're participants in the cosmos, not its focal point. This Copernican principle, the idea that we're not central or special, has guided scientific thinking ever since. When an apple falls from a tree, why does it fall down rather than up or sideways? The question seems trivial until you truly think about it. What is gravity? Why do things fall? Why do planets orbit the Sun? These questions occupied the greatest minds for centuries, and it was Isaac Newton, working in England in the late 17th century, who provided answers so fundamental they shaped physics for over 200 years. Newton's first law of motion states that an object at rest stays at rest, and an object in motion continues moving at constant velocity in a straight line, unless acted upon by an external force. This seems counterintuitive because on Earth, friction constantly slows moving objects. But Newton recognized that the tendency to slow down comes from forces like air resistance and friction, not from motion itself. In the absence of such forces, motion persists unchanged, a principle called inertia. His second law quantifies how forces affect motion, stating that force equals mass times acceleration. A given force produces more acceleration in a light object than a heavy one. This law allows precise prediction of how objects respond to forces, making it foundational for engineering, from designing bridges to calculating rocket trajectories. Newton's third law states that for every action, there's an equal and opposite reaction. When you push against a wall, the wall pushes back with equal force. When a rocket expels gases backward, those gases push the rocket forward. This law explains phenomena from swimming to jet propulsion. But Newton's crowning achievement was universal gravitation. He realized that the force pulling apples to Earth and the force keeping the moon in orbit around Earth are the same. Gravity is universal, acting between all objects with mass. The gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This simple equation explained an astonishing range of phenomena. It explained why planets orbit in ellipses, as Kepler had discovered but couldn't explain. It explained ocean tides, caused by the moon's and sun's gravitational pull on Earth's waters. It predicted the return of comets, such as the one now called Halley's Comet. It allowed calculation of the mass of planets and the sun from their gravitational effects. It explained why objects fall at the same rate regardless of mass. The gravitational force on a heavy object is larger, but so is its inertia, and these effects exactly cancel out. Newton's laws unified celestial and terrestrial physics. Before Newton, the heavens operated by different rules than Earth. After Newton, one set of laws governed everything. This unification was philosophically profound. The universe operates according to consistent, mathematical laws discoverable through reason and observation. For over 2 centuries, Newtonian mechanics reigned supreme. Engineers used it to design machines, bridges, and buildings. Astronomers used it to predict planetary positions with remarkable accuracy. It seemed complete, absolute truth about motion and gravity. But cracks appeared. Mercury's orbit showed slight anomalies Newtonian gravity couldn't explain. At very high speeds and in strong gravitational fields, predictions deviated slightly from observations. Einstein's general relativity eventually superseded Newton's gravity, showing that gravity isn't a force in the traditional sense, but rather a curvature of space-time caused by mass. Yet Newton's laws remain extraordinarily useful. They're accurate enough for most practical purposes, from launching satellites to designing roller coasters. We still teach them because they work, because they're simpler than relativistic equations for everyday situations, and because they represent a crucial step in humanity's growing understanding of the physical world. Human eyes are remarkable organs, but they have limitations. Distant objects blur into vagueness. tiny structures remain invisible. For hundreds of thousands of years, humans saw only what unaided eyes could show them, a limit that constrained understanding of both the vastly large and the incredibly small. Then, in the early 17th century, Dutch lens makers experimenting with glass opened windows into realms beyond normal vision. The telescope emerged around 1608, with credit typically given to Hans Lippershey, though several people may have independently discovered that combining lenses could magnify distant objects. Galileo Galilei heard about this invention and quickly constructed his own telescope, improving the design to achieve greater magnification. In 1609, he turned his telescope skyward and astronomy transformed overnight. Through his telescope, Galileo saw mountains and craters on the moon, revealing it as a world with terrain rather than a smooth celestial sphere. He discovered 4 moons orbiting Jupiter, now called the Galilean moons: Io, Europa, Ganymede, and Callisto, proving that not everything orbited Earth. He observed phases of Venus, conclusive evidence for the heliocentric model. He resolved the Milky Way into countless individual stars. He saw sunspots crossing the sun's face. Each observation challenged prevailing cosmology and demonstrated that the universe contained wonders invisible to naked eyes. Telescopes improved steadily. Kepler designed better arrangements of lenses. Newton created reflecting telescopes using mirrors instead of lenses, avoiding chromatic aberration, the colored halos produced by refracting light through glass. Larger mirrors and lenses collected more light, revealing fainter objects. Better glass and grinding techniques improved image clarity. By the 18th and 19th centuries, telescopes were revealing the true scale of the cosmos. William Herschel discovered Uranus, the first planet found with a telescope. Astronomers cataloged thousands of nebulae. Some were stellar clusters, others vast clouds of gas, still others entire galaxies beyond our own. Spectroscopy, combined with telescopes, revealed stellar composition and temperatures. Photography allowed long exposures that accumulated light from extremely distant objects. Modern telescopes have become engineering marvels. The Hubble Space Telescope orbits above Earth's atmosphere, capturing images of unprecedented clarity, peering billions of light years into space, and thus billions of years into the past. Ground-based telescopes have grown enormous. The Grand Telescopio Canarias has a mirror over 10 meters in diameter, and even larger instruments are under construction. Radio telescopes detect electromagnetic radiation invisible to human eyes, revealing cosmic phenomena like pulsars and mapping hydrogen throughout galaxies. Telescopes operating at infrared, ultraviolet, X-ray, and gamma-ray wavelengths each reveal different aspects of the universe. While telescopes explored the very large, microscopes revealed the very small. The compound microscope, using multiple lenses to achieve higher magnification, appeared around 1590, probably invented by Dutch spectacle makers Zacharias and Hans Janssen. Early microscopes were curiosities, revealing details of insects and plant structures that astonished observers but weren't yet tied to scientific understanding. Antony van Leeuwenhoek revolutionized microscopy in the late 17th century. Though not formally trained as a scientist, he ground lenses with exceptional skill, achieving magnifications over 200 times. With these powerful, simple microscopes, using single, carefully ground lenses, he discovered a hidden world. He observed bacteria, animalcules he called them, in water, in his own mouth, in material scraped from teeth. He saw blood cells flowing through capillaries. He examined sperm cells and plant cells. He described protozoa and rotifers. His meticulous observations and detailed illustrations revealed that life existed at scales far below what anyone had imagined. Robert Hooke, using a compound microscope, published Micrographia in 1665, filled with detailed illustrations of objects under magnification. He coined the term cell after observing the box-like structures in cork, which reminded him of monastery cells. Though he saw only cell walls of dead tissue, not living cells, his work popularized microscopy and demonstrated its potential for scientific discovery. As microscopes improved through the 18th and 19th centuries, they became indispensable for biology and medicine. Scientists discovered that all living things are composed of cells. They observed cell division and began understanding reproduction. They identified bacteria as causes of disease, revolutionizing medicine. They studied tissues and organs at microscopic levels, understanding anatomy in new detail. The light microscope has fundamental limits. It cannot resolve details smaller than the wavelength of light itself, roughly 200 nanometers. 20th century innovations pushed beyond this barrier. The electron microscope, developed in the 1930s, uses beams of electrons instead of light, achieving magnifications over 10 million times and resolving details down to fractions of a nanometer. Scanning probe microscopes can image individual atoms. These instruments have revealed viruses, protein structures, molecular machinery inside cells, and the atomic architecture of materials. Telescopes and microscopes share a conceptual kinship. Both extend human perception beyond its natural limits. Both reveal that reality contains structures and phenomena at scales we cannot directly experience. Together, they demonstrated that the universe is vaster and more intricate than our senses alone could ever know, that understanding requires tools to augment perception, and that invisible realms, both the cosmic and the microscopic, follow laws we can discover and comprehend. Air seems like nothing. We move through it effortlessly. We rarely think about its weight pressing down on us from all directions. Yet the discovery that air has substance and exerts pressure opened up new understanding of weather, breathing, fluid dynamics, and countless technologies from barometers to vacuum pumps. Ancient and medieval thinkers generally believed that nature abhors a vacuum, that empty space cannot exist, and if you try to create it, nature rushes to fill it. This explained why water rises when you suck on a straw, or why pumps can lift water. But it didn't explain why there were limits. Galileo noted that suction pumps couldn't lift water higher than about 10 meters, but he didn't solve the puzzle before he died. Evangelista Torricelli, Galileo's assistant and successor, solved it in 1643. He filled a long glass tube with mercury, sealed one end, then inverted it into a dish of mercury. The mercury in the tube fell to a height of about 76 centimeters, leaving an apparent vacuum above it. Torricelli realized that atmospheric pressure, the weight of air pressing down on the mercury in the dish, supported the column of mercury in the tube. The space above the mercury was the first laboratory-created vacuum, though not perfect. Torricelli's barometer not only proved air has weight, but also showed that atmospheric pressure varies. The mercury column's height changed day to day, and he speculated this related to weather changes. Indeed, Falling barometric pressure often precedes storms, while rising pressure indicates clearing weather. Barometers became essential instruments for weather prediction. Blaise Pascal extended Torricelli's findings. He reasoned that if air's weight causes atmospheric pressure, then pressure should decrease at higher altitudes where there's less air above. In 1648, he arranged an experiment where barometers were carried up Puy de Dôme, a mountain in France. As predicted, the mercury column decreased at higher elevations, proving that atmospheric pressure results from air's weight. Otto von Guericke dramatically demonstrated atmospheric pressure's force in 1654 with the Magdeburg hemispheres. He created two bronze hemispheres that fit together to form a sphere, pumped out the air inside, and showed that 16 horses, 8 pulling each direction, couldn't pull the hemispheres apart. Once air was let back in, they separated easily. The demonstration vividly showed that air pressure, acting over the sphere's surface area, creates enormous force. Robert Boyle, working with Robert Hooke, improved the vacuum pump and used it to explore air's properties. Boyle's law states that at constant temperature, gas pressure and volume are inversely related. If you have the volume, you double the pressure. This quantitative relationship was crucial for understanding gas behavior. Understanding atmospheric pressure enabled numerous technologies and insights. It explained how breathing works. The diaphragm expands the chest cavity, reducing pressure so air rushes in. Contraction increases pressure, pushing air out. It explained how siphons work, how steam engines operate, how weather systems move. Pressure cooking, pneumatic tools, diving equipment, air conditioning, all depend on controlling air pressure. The discovery that we live at the bottom of an ocean of air, with roughly 10 metric tons of atmosphere pressing on each square meter of Earth's surface, fundamentally changed how we understand our environment. It showed that what seems like nothing, air, is actually something quite substantial, and that our intuitions about how fluids behave need refinement through careful observation and experimentation. One of the most fundamental principles in science is that you can't create something from nothing or destroy something into nothingness. Matter can change form, rearrange into new configurations, convert between different states, but the total amount remains constant. This principle, conservation of mass, seems almost intuitive today, but establishing it required careful experimentation that challenged prevailing theories. For much of history, processes like burning seemed to violate mass conservation. Burn a piece of wood, and you get ash weighing far less than the original wood. Where did the mass go? The phlogiston theory, popular in the 17th and 18th centuries, proposed that combustible materials contain a substance called phlogiston that escapes during burning. This theory explained many observations, but ultimately proved incorrect. Antoine Lavoisier established conservation of mass through meticulous experiments in the 1770s and 1780s. Working in Paris, he conducted combustion experiments in sealed containers where nothing could enter or escape. He carefully weighed everything before and after reactions. When metals burned, they gained mass rather than losing it, combining with air, specifically oxygen, which Lavoisier helped identify. When organic materials burned, they produced gases, carbon dioxide and water vapor, that could be captured and weighed. In all cases, the total mass before and after reactions remained constant. Lavoisier's experiments demolished the phlogiston theory. Combustion wasn't a substance escaping, but rather combination with oxygen from air. The apparent loss of mass when wood burned occurred because gases escaped. Capture those gases and weigh them, and total mass is conserved. Conservation of mass became a cornerstone of chemistry. Chemical equations must balance, the same elements appearing on both sides in the same quantities. This principle enabled stoichiometry, calculating exact amounts of reactants needed and products produced in chemical reactions. It allowed chemists to determine atomic weights by measuring how much of each element combines with others. The principle seemed absolute until the early 20th century, when Einstein's special relativity revealed that mass and energy are interconvertible through the famous equation E=mc². In nuclear reactions, tiny amounts of mass convert to enormous amounts of energy, and high-energy photons can create particle-antiparticle pairs from nothing but energy. Even chemical reactions involve infinitesimal mass changes. Exothermic reactions release energy and thus lose an immeasurably tiny amount of mass. Yet for ordinary chemistry and everyday life, mass conservation holds with extraordinary precision. The mass changes in chemical reactions are so small, parts per billion, that they're undetectable with ordinary instruments. Conservation of mass remains a practical law that chemists, engineers, and scientists rely on constantly. It reflects a deeper principle: conservation of energy mass, where the total energy, including rest mass energy, remains constant in closed systems. This discovery exemplifies how science progresses. An approximate idea, matter seems fairly constant, became a precise principle through careful measurement. That principle proved incredibly useful and accurate within its domain. Then deeper investigation revealed it as a special case of a more fundamental principle. Yet the approximate law remains perfectly adequate for most purposes. Lavoisier's work established that chemistry could be quantitative, predictable, and precise, transforming it from a partly mystical art into a rigorous science. Why do things burn? What is fire? For millennia, these questions lacked satisfactory answers. Fire seemed almost magical, a transformative force that could be produced through friction or striking stones, but whose essential nature remained mysterious. The discovery of oxygen and the true nature of combustion represented a pivotal moment in chemistry, replacing ancient misconceptions with genuine understanding. The phlogiston theory, dominant in the 18th century, held that all combustible materials contain phlogiston, released during burning. The theory explained many observations: why flames go out in closed containers, the air becomes saturated with phlogiston, why charcoal leaves so little residue, it's almost pure phlogiston, but struggled with others, particularly why some substances gain mass when burned. Several chemists isolated oxygen before understanding its significance. Carl Wilhelm Scheele in Sweden produced oxygen in 1772 by heating various compounds, though he interpreted his findings through phlogiston theory. Joseph Priestley in England isolated oxygen in 1774 by heating mercury oxide and noted that candles burned brighter in it and mice lived longer. He called it dephlogisticated air, thinking it especially capable of absorbing phlogiston. Antoine Lavoisier recognized oxygen's true significance. Through careful experiments, he showed that combustion involves combination with oxygen from air, not release of phlogiston. When metals burn, they gain mass by combining with oxygen. When organic materials burn, they combine with oxygen to form carbon dioxide and water. Breathing, he showed, is a form of slow combustion. Animals consume oxygen and produce carbon dioxide, using the energy released to power bodily functions. Lavoisier named the element oxygen, from Greek words meaning acid former, because he mistakenly believed all acids contain oxygen. Despite this error, his broader understanding was correct. He published his new theory of combustion in 1777, and over the following years, the phlogiston theory collapsed as chemists recognized oxygen theory's superior explanatory power. Understanding oxygen revolutionized chemistry and biology. It explained respiration, why animals need air, and why we exhale carbon dioxide. It explained fermentation and decay as processes involving oxygen consumption or exclusion. It enabled understanding of how oxygen cycles through ecosystems. Plants produce it through photosynthesis, animals consume it through respiration, and combustion and decay processes consume it, with the cycle balanced globally. Oxygen makes up about 21% of Earth's atmosphere, generated primarily by photosynthetic organisms. This seems natural, but Earth's early atmosphere contained virtually no oxygen. Oxygen built up gradually over billions of years as photosynthetic bacteria and later plants released it. The Great Oxidation Event, around 2.4 billion years ago, saw atmospheric oxygen rise dramatically, fundamentally changing Earth's chemistry and enabling the evolution of complex, oxygen-breathing life. Oxygen is highly reactive, combining with most elements. This reactivity makes it essential for metabolism. Organisms extract energy by oxidizing food molecules in controlled ways. It also makes oxygen corrosive, iron rusts, organic materials decay. Life has evolved elaborate mechanisms to harness oxygen's reactivity while protecting against its damaging effects. Medically, oxygen is crucial. Hypoxia, insufficient oxygen, quickly causes tissue damage and can be fatal. Supplemental oxygen treats respiratory conditions, supports premature infants, aids recovery from carbon monoxide poisoning. Hyperbaric oxygen therapy uses high-pressure oxygen to treat decompression sickness and promote wound healing. The discovery of oxygen and combustion's true nature exemplifies scientific revolution, not just adding new facts, but overthrowing an entire theoretical framework and replacing it with a more accurate one. It showed that phenomena seeming to involve substance release actually involve substance absorption. It demonstrated that weight changes during reactions provide crucial clues to what's actually happening. It established that understanding nature requires rejecting comfortable theories when evidence contradicts them, even if new theories seem initially strange or counterintuitive. Everything around us, water, air, rocks, living tissue, is made of matter. But what is matter made of? Can you keep dividing it forever into smaller pieces? Or is there a smallest indivisible unit? Ancient Greek philosophers debated this question. Democritus proposed that matter consists of tiny, indivisible particles called atoms moving through empty space. Aristotle rejected this view, favoring continuous matter that could be infinitely divided. For over 2,000 years, Aristotle's view dominated Western thought. John Dalton revived and refined atomic theory in the early 1800s, placing it on firm empirical foundation. Working in England, Dalton studied gases and chemical reactions, noting patterns in how elements combine. He formulated several key principles. First, all matter consists of tiny, indivisible atoms. Second, All atoms of a given element are identical in mass and properties, while atoms of different elements differ. Third, atoms combine in simple whole number ratios to form compounds. Fourth, chemical reactions rearrange atoms, but don't create or destroy them. Dalton's atomic theory explained numerous observations. The law of definite proportions. Compounds always contain the same elements in the same mass ratios. Made sense if compounds form from specific numbers of specific atoms. The law of multiple proportions. When two elements form multiple compounds, the mass ratios follow simple whole number patterns. Made sense if compounds differ in how many atoms of each type they contain. Atomic theory enabled chemistry to become truly scientific. Chemists could write formulas showing atomic composition. H2O for water means two hydrogen atoms bonded to one oxygen atom. Chemical equations could show exactly how atoms rearrange during reactions. Stoichiometry allowed precise predictions of how much reactant is needed in product produced. Yet Dalton's theory had limitations. Atoms aren't actually indivisible. They contain subatomic particles. Not all atoms of an element are identical. Isotopes have different masses. Atoms can convert into other elements through nuclear reactions. But these refinements came later and didn't undermine atomic theory's core insight. Matter has fundamental building blocks whose properties determine chemical behavior. The 19th century saw accumulating evidence for atoms. Kinetic theory explained gas behavior by treating gases as collections of countless tiny particles in constant motion. Brownian motion, the random jittering of pollen grains suspended in water, observed by Robert Brown in 1827, was explained by Einstein in 1905 as resulting from collisions with water molecules, providing visible evidence that molecules exist. Direct proof of atoms came in the early 20th century. J.J. Thomson discovered electrons in 1897, showing atoms contain even smaller particles. Ernest Rutherford's gold foil experiment in 1909 revealed that atoms have tiny, dense nuclei. Niels Bohr developed a quantum model of atomic structure. X-ray crystallography revealed atomic arrangements in crystals. Scanning tunneling microscopes eventually allowed us to image individual atoms. Modern atomic theory is far more sophisticated than Dalton's. We understand atoms as quantum mechanical systems with electrons existing in probability clouds around nuclei composed of protons and neutrons, which themselves consist of quarks. We know about isotopes, ions, atomic spectra, radioactive decay, nuclear reactions. Yet Dalton's basic insight remains valid. Matter consists of discrete atomic units whose arrangement and interactions determine material properties. Atomic theory transformed not just chemistry, but all of science and technology. Materials science engineers materials at atomic levels. Nanotechnology manipulates individual atoms and molecules. Nuclear power and weapons harness energy from atomic nuclei. Quantum computers exploit atomic-scale quantum phenomena. Medicine uses radioactive isotopes for imaging and treatment. Understanding atoms unlocked the ability to manipulate matter with unprecedented precision, transforming the natural world from something we simply use into something we can redesign at the most fundamental levels. By the mid-19th century, chemists had identified over 60 elements, substances that couldn't be broken down into simpler components. Each element had unique properties. Some were metals, others gases or nonmetals. Some reacted vigorously with water, others barely reacted with anything. The growing list seemed chaotic, lacking organizing principles. Then several scientists began noticing patterns, and Dmitry Mendeleev created a framework that revealed deep order underlying chemical diversity. Earlier attempts at classification had limited success. Johann Dobereiner noted triads of elements with similar properties whose atomic weights formed arithmetic sequences. John Newlands proposed the law of octaves, noting that every eighth element in order of atomic weight shared similar properties. But these patterns were incomplete and didn't accommodate all known elements. Mendeleev, working in Russia, took a more comprehensive approach. In 1869, he arranged elements in order of increasing atomic weight and grouped those with similar properties into columns. His periodic table revealed that chemical properties recur periodically. Hence, periodic table. Elements in the same column, group, share similar chemical behaviors. Alkali metals in Group 1 are soft, highly reactive metals. Noble gases in Group 18 are inert, rarely forming compounds. Halogens in Group 17 are reactive nonmetals. Mendeleev's genius lay not just in arrangement, but in bold predictions. When gaps appeared where no known element fit the pattern, he predicted undiscovered elements, specifying their properties in detail. He predicted EKA silicon, later discovered as germanium, matching his predictions remarkably. He predicted EKA aluminum, gallium, and EKA boron, scandium. As these predictions proved accurate, the periodic table gained credibility and became chemistry's central organizing principle. The periodic table wasn't merely organizational. It revealed something fundamental about matter. Why do properties recur periodically? Mendeleev couldn't explain this, but 20th century quantum mechanics did. Elements in the same group have the same number of electrons in their outermost shell, and these valence electrons determine chemical behavior. The periodic table reflects electron configuration patterns arising from quantum mechanical laws governing how electrons arrange themselves around nuclei. The modern periodic table differs slightly from Mendeleev's. Elements are ordered by atomic number of protons, rather than atomic weight, resolving anomalies where atomic weight order didn't match chemical properties. Additional groups accommodate newly discovered elements, lanthanides, actinides, synthetic elements created in laboratories. As of today, 118 elements are confirmed, with searches continuing for higher-numbered elements. The periodic table connects to nearly every aspect of chemistry and materials science. It explains why sodium and chlorine, each dangerous separately, combine to form harmless table salt. It predicts what types of compounds elements can form and how stable those compounds will be. It guides searches for new materials with desired properties. It helps explain biological processes, why hemoglobin binds oxygen, how enzymes catalyze reactions, why certain elements are essential nutrients while others are toxic. The periodic table represents one of science's great unifying achievements, revealing that seemingly diverse phenomena follow common principles. It shows that nature operates according to elegant patterns discoverable through careful observation and reasoning. It demonstrates that classification systems aren't arbitrary human impositions, but can reflect genuine natural order. Every chemistry classroom displays the periodic table, a testament to Mendeleev's insight and the deep regularities underlying chemical reality. For centuries, electricity and magnetism seemed separate phenomena. Lodestones attracted iron, Rubbing amber generated sparks. Lightning struck during storms. These effects seemed unrelated, curiosities of nature without obvious connection. The discovery that electricity and magnetism are intimately related. Different manifestations of the electromagnetic force ranks among physics' greatest unifications, revealing that seemingly distinct phenomena share a common origin. Ancient peoples knew about both electricity and magnetism. Greeks discovered that rubbing amber attracts small objects. The word electricity derives from elektron, Greek for amber. Chinese discovered that lodestones align north-south and used this for navigation. But systematic investigation came much later. In the 18th century, experiments revealed electricity's properties. Benjamin Franklin showed that lightning is electrical, proved in his famous and dangerous kite experiment in 1752. He introduced concepts of positive and negative charge and showed they cancel each other out. Charles Augustin de Coulomb quantified the force between charges. Like charges repel, opposite charges attract, with force proportional to charge magnitudes and inversely proportional to distance squared. Hans Christian Ørsted made the crucial discovery connecting electricity and magnetism in 1820. He noticed that electric current flowing through a wire deflected a nearby compass needle. This was astonishing. Electricity produced magnetic effects. André-Marie Ampère quickly followed up, showing that parallel currents attract or repel depending on their directions, and developing mathematical laws describing magnetic forces from currents. Michael Faraday, working in England, discovered electromagnetic induction in 1831. He showed that changing magnetic fields generate electric currents. Move a magnet near a wire coil and current flows in the coil. This principle underlies electric generators, transformers, and countless technologies. Faraday also introduced field theory, imagining space filled with invisible lines of force rather than action at a distance. This conceptual shift proved profound. James Clerk Maxwell unified electricity and magnetism into a comprehensive mathematical theory in the 1860s. Maxwell's equations describe how electric and magnetic fields interact and propagate. Changing electric fields create magnetic fields. Changing magnetic fields create electric fields. These coupled fields can sustain each other, propagating through space as electromagnetic waves at the speed of light. Maxwell realized that light itself is an electromagnetic wave. His equations predicted electromagnetic waves at all frequencies, not just visible light, but radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. This prediction was spectacularly confirmed when Heinrich Hertz generated and detected radio waves in 1887, proving electromagnetic waves exist beyond visible spectrum. Understanding electromagnetism enabled the Second Industrial Revolution. Electric generators convert mechanical motion into electricity using electromagnetic induction. Electric motors reverse the process, converting electricity into motion. Transformers use electromagnetic induction to change voltage levels, enabling long-distance power transmission. Radio and television transmit information via electromagnetic waves. Computers process information using electromagnetic phenomena in semiconductors. Electromagnetism shapes our everyday experience far more than most people realize. Light allowing us to see is electromagnetic. All chemistry involves electromagnetic interactions between electrons and nuclei. Solidity. Why you don't fall through the floor. arises from electromagnetic repulsion between electron clouds and atoms. Color, texture, temperature, sensation all involve electromagnetism. Of nature's four fundamental forces, gravity, electromagnetism, strong nuclear, weak nuclear, electromagnetism governs most phenomena we directly experience. The unification of electricity and magnetism inspired subsequent unification efforts. 20th century physicists unified electromagnetism with the weak nuclear force into the electroweak force. Attempts continue to unify all fundamental forces into a single framework, a theory of everything. Whether or not complete unification is achieved, electromagnetism remains central to physical understanding, and Maxwell's elegant equations remain among physics' greatest achievements, comparable in significance to Newton's laws or Einstein's relativity. Energy flows through the universe in countless ways. A fire radiates heat. An engine burns fuel to produce motion. Living things consume food to power their activities. For much of history, heat, work, and energy seemed only loosely related. The development of thermodynamics in the 19th century revealed profound principles governing all energy transformations, principles that constrain what's possible and impossible in our universe. The first law of thermodynamics states that energy is conserved. It can change form, but cannot be created or destroyed. This seems similar to mass conservation, but 19th century scientists gradually realized that heat is a form of energy, not a substance. James Prescott Joule demonstrated through careful experiments in the 1840s that mechanical work can be converted to heat at a fixed rate, the mechanical equivalent of heat. A specific amount of work always produces the same amount of heat. This suggested that work and heat are interconvertible forms of something more fundamental, energy. Energy conservation has profound implications. Perpetual motion machines, devices producing work without energy input, are impossible. Any process must account for energy inputs and outputs. Chemical reactions release or absorb energy, but the total energy before and after remains constant. Nuclear reactions convert mass into energy, but the total mass energy is conserved. The second law of thermodynamics is deeper and more subtle. It states that entropy, roughly, disorder or randomness, never decreases in isolated systems. Heat flows spontaneously from hot to cold, not cold to hot. Gas expands to fill containers, never spontaneously concentrating in one corner. Broken eggs don't spontaneously reassemble. There's an arrow of time built into thermodynamics. Processes that increase entropy occur spontaneously. Those that decrease entropy require external energy input. Rudolf Clausius formulated the second law mathematically in the 1850s, introducing the concept of entropy. Ludwig Boltzmann later connected entropy to probability. Systems evolve toward more probable states, and disordered states are vastly more probable than ordered ones. There are countless ways to scramble an egg, but only one way to have it perfectly intact. The second law isn't absolute. Entropy can temporarily decrease in part of a system if it increases more elsewhere. But the universal trend toward increasing entropy shapes reality profoundly. The second law explains why heat engines have maximum efficiencies determined by temperature differences between hot and cold reservoirs. Sadi Carnot established these limits in the 1820s while studying steam engines. No engine can be more efficient than a Carnot engine operating between the same temperatures. This isn't an engineering limitation, but a fundamental constraint from thermodynamics. The third law of thermodynamics states that absolute zero, 0 Kelvin, negative 273.15 degrees Celsius, cannot be reached. You can approach it arbitrarily closely, but never quite get there. At absolute zero, a perfect crystal would have zero entropy, but reaching this state would require infinite process steps. Thermodynamics has vast implications beyond heat engines. It governs chemical reactions. Reactions spontaneously proceed in directions that increase total entropy. It constrains living things. Organisms maintain low internal entropy, high order, only by increasing entropy in their surroundings, consuming organized energy sources like sunlight or food, and releasing disordered heat. The universe itself obeys thermodynamics. It evolves toward states of higher entropy, eventually reaching heat death, where all temperature differences vanish and no useful work can be extracted. Yet thermodynamics says nothing about how fast processes occur, only whether they're possible and which direction they'll go. That's where kinetics and specific mechanisms come in. Thermodynamics tells us a diamond will eventually turn into graphite, lower energy, higher entropy, but doesn't mention this takes billions of years under normal conditions. The laws of thermodynamics are among the most universal principles in science. Einstein reportedly said concerning the first and second laws, "A theory is the more impressive the greater the simplicity of its premises, the more different kinds of things it relates, and the more extended its area of applicability." Therefore, the deep impression that classical thermodynamics made upon me. It is the only physical theory of universal content which I am convinced will never be overthrown. Why do children resemble their parents? How are traits passed from one generation to the next? These questions occupied thinkers for millennia. Ancient theories proposed blending inheritance, offspring as mixtures of parental characteristics. This seemed reasonable but created problems. If traits blended, variation should diminish each generation, yet it doesn't. Rare traits should disappear, yet they persist. The true mechanism of inheritance remained mysterious until Gregor Mendel's experiments revealed that heredity follows mathematical laws. Mendel, an Augustinian friar working in the monastery garden at Brno, now in the Czech Republic, conducted meticulous experiments with pea plants from 1856 to 1863. He chose peas for their rapid growth, distinct traits, and ease of controlled breeding. He focused on traits like seed shape, round or wrinkled, seed color, yellow or green, flower color, purple or white, and plant height, tall or short. Mendel cross-pollinated plants with contrasting traits and tracked how traits appeared in offspring over multiple generations. His experiments revealed clear patterns. When he crossed purebred plants differing in one trait, say, tall plants with short plants, all first-generation offspring showed only one variant, all tall. But when these hybrids self-pollinated, the hidden trait reappeared in the next generation in a roughly 3-to-1 ratio, 3 tall plants for every 1 short plant. From these patterns, Mendel deduced several principles. First, traits are determined by paired factors, what we now call genes, one inherited from each parent. Second, when factors differ, one may be dominant, expressed, while the other is recessive, hidden but still present. Third, these factors separate during reproduction, with each offspring inheriting one factor from each parent. Fourth, factors for different traits assort independently. Mendel published his findings in 1866, but they were largely ignored, partly because they appeared in an obscure journal, partly because their mathematical nature was unfamiliar to biologists, partly because Mendel lacked academic prominence. Only after his death, when three scientists independently rediscovered similar patterns around 1900, was Mendel's work recognized as foundational. The rediscovery launched genetics as a scientific discipline. Scientists realized Mendel's factors, soon called genes, exist physically. Thomas Hunt Morgan and colleagues working with fruit flies in the early 1900s showed that genes reside on chromosomes, located at specific positions. They mapped genes by studying how traits are inherited together, establishing chromosome theory of inheritance. Understanding inheritance revolutionized biology and agriculture. Breeders could predict offspring traits statistically and develop new crop varieties and animal breeds systematically rather than through trial and error. The Punnett square, introduced by Reginald Punnett, provided a simple tool for predicting inheritance patterns. Mendelian genetics also had social implications, unfortunately including misuse. Eugenics movements proposed improving human populations through selective breeding, based on misunderstandings of genetics and racist/classist assumptions. These ideas contributed to horrific policies including forced sterilizations and, ultimately, Nazi atrocities. Understanding genetics' proper scope and limitations remains crucial. Genes influence traits, but don't deterministically dictate them. Environmental factors matter enormously. Human value doesn't derive from genetic makeup. Modern genetics has revealed complexities beyond Mendel's simple model. Many traits involve multiple genes, polygenic inheritance. Some genes show incomplete dominance or codominance. Gene expression can be modified by environmental factors, epigenetics. Genes themselves can mutate, creating new variants. But Mendel's core insights remain valid. Inheritance involves discrete factors passed from parents to offspring according to statistical laws, not blending of characteristics. Mendel's work exemplifies the power of quantitative thinking in biology. By counting offspring, calculating ratios, and applying mathematical analysis to living systems, he revealed underlying order in phenomena that seemed hopelessly complex. His patient experimentation, spanning 7 years and involving thousands of plants, demonstrated that biological understanding requires the same careful measurement and statistical analysis as physics or chemistry. Few scientific theories have transformed human self-understanding as profoundly as evolution by natural selection. The realization that all living things share common ancestry, that species change over time through natural processes, that humans emerge through the same evolutionary forces that shaped all life. These ideas challenged prevailing beliefs about humanity's place in nature and provided a unifying framework for all biological sciences. Evidence for evolution accumulated before anyone explained how it occurred. Fossils showed extinct species different from modern ones. Georges Cuvier established that species can go extinct. Rock layers revealed a succession of different life forms over time. Similar anatomical structures in different species, like the bones in human arms, bat wings, and whale flippers, suggested common ancestry. Geographic distribution of species showed patterns. Similar environments on different continents housed different species, suggesting they evolved locally rather than being specially created for each location. Charles Darwin and Alfred Russel Wallace independently developed the theory of natural selection in the mid-19th century. Darwin, after serving as naturalist on HMS Beagle's voyage around the world from 1831 to 1836, spent over 20 years gathering evidence and refining his theory. Wallace, working in Southeast Asia, reached similar conclusions. Both were influenced by Thomas Malthus's observation that populations can grow faster than food supply, leading to competition. Natural selection operates through several key principles. First, organisms produce more offspring than can survive to reproduce. Second, individuals vary in their traits, and some variations are heritable. Third, competition for limited resources creates differential survival and reproduction. Some individuals are better suited to their environment and leave more offspring. Fourth, over many generations, traits beneficial for survival and reproduction become more common, while less beneficial traits become rarer. Darwin published On the Origin of Species in 1859, presenting extensive evidence for evolution and natural selection. The book's impact was immediate and controversial. It challenged the prevailing belief in species immutability and special creation. It suggested that humans, rather than being fundamentally different from other life, arose through the same evolutionary processes. Religious authorities objected, though many theologians eventually reconciled evolution with faith. Evidence for evolution has become overwhelming. The fossil record shows gradual changes in species over time, with transitional forms connecting major groups: fish to amphibians, reptiles to mammals, land mammals to whales. Comparative anatomy reveals homologous structures indicating common ancestry. Embryonic development shows similarities across diverse species, with early embryos of vertebrates remarkably similar. Geographic distribution makes sense in light of evolution. Island species resemble nearby mainland species, adapted to local conditions. Molecular biology provides perhaps the strongest evidence. DNA sequences show patterns of similarity matching evolutionary relationships predicted from anatomy and fossils. All living things use the same genetic code, the same biochemical pathways, suggesting common ancestry. Vestigial structures, like human tailbones or whale hip bones, make sense as evolutionary remnants but are puzzling in special creation. Natural selection explains adaptation, how organisms develop features suited to their environments. Polar bears have white fur for camouflage in snow. Desert plants have extensive roots and water-storing tissues. Predators have forward-facing eyes for depth perception. Prey have side-mounted eyes for wide vision. Each adaptation arose because individuals with those traits survived and reproduced more successfully. Evolution also explains puzzling features. Why do humans get goosebumps? Because our ancestors had fur that could be raised for insulation or threat display. The mechanism persists though the fur is gone. Why do whales have hip bones? Because their ancestors were land mammals that returned to the sea, and these bones are evolutionary remnants. Why are there so many species of beetles? Because successful groups diversify into many ecological niches. Natural selection isn't the only evolutionary mechanism. Genetic drift, random changes in gene frequencies, affect small populations. Gene flow introduces variation through migration. Mutation creates new genetic variants. Sexual selection favors traits that attract mates, even if they're otherwise disadvantageous, like peacock tails. but natural selection remains the primary driver of adaptation. Evolution is ongoing, observable in real time. Bacteria evolve antibiotic resistance within years. Insects develop pesticide resistance. HIV evolves drug resistance in individual patients. Darwin's finches in the Galapagos show measurable evolutionary changes from generation to generation in response to environmental fluctuations. Experimental evolution in laboratories demonstrates selection, creating new adaptations within hundreds of generations. Understanding evolution transformed biology from a catalog of facts into an integrated science. Nothing in biology makes complete sense except in light of evolution, as Theodosius Dobzhansky famously said. Why do organisms share biochemical pathways? Common ancestry. Why do embryos show peculiar stages? Evolutionary history. Why do pathogens emerge? Evolution. Why must we keep developing new antibiotics? Evolution. Medicine, agriculture, conservation all depend on evolutionary understanding. Evolution also raises philosophical questions. If humans evolved from earlier primates, sharing ancestors with all life, what does this mean for human uniqueness and dignity? Most people, including religious believers, have concluded that evolutionary origins don't diminish human value or significance. How we arose doesn't determine what we are or can become. Evolution describes the process that shaped life's diversity. It doesn't address purpose, meaning, or ethics, which require other frameworks of thought. For most of human history, disease seemed mysterious, capricious, and often attributed to supernatural causes, punishment from gods, malevolent spirits, miasma, bad air, or imbalance of bodily humors. People noticed that disease could spread from person to person, but didn't understand how. The discovery that many diseases are caused by microscopic organisms, bacteria, viruses, fungi, and parasites, revolutionized medicine, public health, and human welfare. The idea that invisible organisms cause disease emerged gradually. Antony van Leeuwenhoek observed bacteria through his microscopes in the late 17th century, but connecting these animalcules to disease took another 2 centuries. In the 19th century, several scientists contributed pieces to the puzzle. Ignaz Semmelweis, working in a Vienna hospital in the 1840s, noticed that women giving birth attended by doctors died from childbed fever far more often than those attended by midwives. Doctors typically came straight from autopsy rooms without washing hands. Semmelweis instituted hand washing with chlorinated lime solution, and mortality rates plummeted. Despite the evidence, his findings were rejected by the medical establishment, partly because germ theory didn't yet exist to explain them. Semmelweis died in an asylum, his discovery unrecognized, though later vindication came. Louis Pasteur provided crucial evidence for germ theory through experiments on fermentation and spoilage in the 1850s and 1860s. He showed that microorganisms cause wine and milk to spoil and that heating, pasteurization, kills them, preventing spoilage. He demonstrated that microbes don't spontaneously generate but come from other microbes. He extended these findings to disease, showing that silkworm diseases were caused by specific microorganisms. He developed vaccines against chicken cholera and anthrax, proving that specific microbes cause specific diseases. Robert Koch established rigorous criteria, now called Koch's postulates, for proving that a specific microorganism causes a specific disease. First, The organism must be present in all cases of the disease. Second, it must be isolated from diseased hosts and grown in pure culture. Third, the cultured organism must cause disease when introduced to healthy hosts. Fourth, the organism must be re-isolated from experimentally infected hosts. Koch identified bacteria causing tuberculosis, cholera, and anthrax, definitively linking specific microbes to specific diseases. Germ theory transformed medicine and public health. If microorganisms cause diseases, then preventing their transmission prevents disease. Hand washing, sterilizing surgical instruments, disinfecting wounds, isolating infectious patients, treating water supplies, improving sanitation, all became standard practices. Before antiseptic techniques, surgical patients often died from infections. Afterward, survival rates soared. Understanding disease transmission led to public health measures that saved countless lives. Clean water systems prevented cholera and typhoid. Sewage treatment reduced disease spread. Food safety regulations prevented bacterial contamination. Quarantine measures controlled epidemic outbreaks. Vaccination programs eliminated or greatly reduced diseases like smallpox, polio, measles, and whooping cough. The germ theory also explained phenomena that had puzzled physicians. Why do epidemics occur? Pathogens spread through populations. Why does disease cluster in families? Close contact enables transmission. Why do some people survive diseases that kill others? Immune system differences and prior exposure. Why do wounds get infected? Bacteria enter breaks in skin. Discovering specific pathogens enabled targeted treatments. Antibiotics kill bacteria, though resistance is an ever-present challenge. Antivirals combat certain viral infections. Antiparasitic drugs treat malaria, worms, and other parasitic diseases. Antifungals address fungal infections. Each discovery of a new pathogen potentially enables development of preventions and cures. Germ theory has limitations. Not all diseases are infectious. Cancer, genetic disorders, autoimmune conditions, degenerative diseases have other causes. Even infectious diseases involve complex interactions between pathogen, host immune system, and environmental factors. The same pathogen may cause severe disease in one person and mild symptoms in another. Understanding disease requires considering multiple factors, not just identifying pathogens. Yet germ theory remains one of medicine's foundational principles. The dramatic increase in human life expectancy over the past century owes much to conquering infectious diseases through vaccines, antibiotics, and public health measures based on germ theory. Diseases that once killed millions, plague, cholera, tuberculosis, diphtheria, are now rare or treatable in most of the world, though they still threaten regions lacking access to modern medicine and public health infrastructure. Louis Pasteur's contributions to science extended far beyond theory into practical applications that transformed food safety and preservation. Pasteurization, heating foods to temperatures that kill most harmful microorganisms without significantly affecting taste or nutritional value, represents one of the most beneficial food processing techniques ever developed, preventing countless illnesses and extending the time food remains safe to consume. Pasteur developed the technique in the 1860s while investigating why French wines were spoiling. He discovered that specific microorganisms caused wine to sour or develop off flavors. Heating wine to temperatures around 60 degrees Celsius for a short time killed these organisms, preserving the wine's quality. The process worked because most disease-causing and spoilage microorganisms die at relatively moderate temperatures, well below water's boiling point, allowing heat treatment without cooking or drastically altering the food. Pasteurization's most significant application became milk. Raw milk, fresh from cows, contains bacteria that cause it to spoil quickly and can harbor pathogens causing tuberculosis, brucellosis, diphtheria, scarlet fever, and severe gastrointestinal illnesses. Before pasteurization became standard, milk-borne diseases killed thousands of children annually. Pasteurizing milk, heating it to at least 72 degrees Celsius for 15 seconds, or other time temperature combinations achieving equivalent bacterial reduction, makes it far safer and extends refrigerated shelf life to several weeks. Pasteurization sparked controversy. Dairy farmers and distributors initially resisted, fearing reduced profits and claiming the process ruined milk's taste and nutritional value. Some argued that disease-causing bacteria in milk came from sick cows and that improving dairy farm sanitation made pasteurization unnecessary. Public health officials countered that while farm sanitation should improve, pasteurization provided essential protection against any contamination occurring during production, handling, or distribution. Evidence eventually prevailed. Cities mandating milk pasteurization saw dramatic declines in milk-borne disease, particularly among children. By the mid-20th century, pasteurization became standard practice in most developed nations. Tuberculosis cases from contaminated milk virtually disappeared. Infant mortality dropped significantly. Milk became a safe, reliable, nutritious food rather than a potential disease vector. Beyond milk, pasteurization applies to many foods and beverages. Fruit juices, beer, wine, canned foods, liquid eggs, all may be pasteurized to kill pathogens and spoilage organisms. Different products require different treatments. Some use high temperature for short time, HDSD, others ultra-high temperature, UHT, for very brief periods, others lower temperatures for longer durations. Pasteurization doesn't sterilize food. It reduces microbial populations to safe levels, but doesn't eliminate all microorganisms. Pasteurized products still require refrigeration and have limited shelf life, unlike sterilized foods which can be stored at room temperature indefinitely. This is actually advantageous for maintaining quality. Sterilization requires much higher temperatures that significantly affect taste, texture, and nutrition. Some people today advocate raw milk consumption, claiming pasteurization destroys beneficial enzymes and nutrients. Research shows pasteurization causes minimal nutritional loss. Vitamin C decreases slightly, but milk isn't a significant vitamin C source anyway. Beneficial bacteria are indeed killed, but they don't survive stomach acid anyway. The risks of raw milk, documented through outbreaks of illness, far outweigh any speculative benefits. Pasteurization exemplifies how scientific understanding translates into practical benefit. By applying germ theory to food safety, Pasteur developed a simple, effective method that saved countless lives. The technique demonstrates that understanding natural processes, in this case, microbial growth and heat susceptibility, enables rational interventions improving human welfare. It also shows the importance of evidence-based policy. Despite initial resistance, the clear benefits of pasteurization led to its widespread adoption, transforming public health. Look at a drop of pond water under a microscope, and you'll see a world of activity. Single-celled organisms swimming, dividing, consuming smaller organisms. Examine your own cheek cells, and you'll see individual cells, each with a nucleus and distinct boundaries. All living things, from bacteria to blue whales, consist of cells, the fundamental units of life. This cell theory, one of biology's most important unifying principles, emerged in the 19th century as microscopy revealed life's cellular structure. Robert Hooke first used the term cell in 1665 when examining thin slices of cork under a microscope. The tiny box-like structures reminded him of monastery cells. However, he was observing dead cell walls in plant tissue, not living cells. Antony van Leeuwenhoek observed living single-celled organisms, bacteria and protozoa, in the late 17th century, but the connection between these and the structure of all living things wasn't yet apparent. The cell theory crystallized in the 1830s and 1840s through work by several scientists. Matthias Schleiden, studying plants, concluded in 1838 that all plant tissues consist of cells. Theodor Schwann extended this to animals in 1839, proposing that all living things are composed of cells. Rudolf Virchow added a crucial component in 1855 with the principle omnis cellula e cellula. Every cell comes from another cell. Cells don't spontaneously generate, but arise only from pre-existing cells dividing. Cell theory comprises several key tenets. First, all living things consist of one or more cells. Second, the cell is life's basic structural and functional unit. Third, all cells come from pre-existing cells. Modern formulations add that cells contain hereditary information, DNA, passed to daughter cells, and that all cells have essentially the same basic chemical composition and metabolic activities. Cells come in enormous variety but share fundamental features. All cells have a membrane separating their interior from the external environment, regulating what enters and exits. All contain genetic information in the form of DNA or RNA in some viruses, though whether viruses are alive is debatable. All carry out basic metabolic processes, obtaining energy, synthesizing molecules, eliminating waste. The distinction between prokaryotic and eukaryotic cells represents one of life's fundamental divisions. Prokaryotic cells, bacteria and archaea, are simple, lacking membrane-bound organelles or nuclei. Their DNA floats freely in the cell. Eukaryotic cells, animals, plants, fungi, and protists, are complex, with DNA enclosed in a nucleus and numerous specialized organelles. Mitochondria for energy production, endoplasmic reticulum for protein synthesis, Golgi apparatus for molecule processing, lysosomes for digestion, and in plants, chloroplasts for photosynthesis. Understanding cells as life's basic units revolutionized biology and medicine. It explained how organisms grow, through cell division and enlargement. It clarified reproduction. Organisms produce offspring by cells dividing and differentiating into new individuals. It illuminated disease. Many disorders involve abnormal cell behavior. Cancer, for instance, results from cells dividing uncontrollably. Diabetes involves insulin-producing cells failing or immune cells attacking them. Understanding disease at the cellular level enables more effective treatments. Cell biology continues revealing life's complexity. Cells aren't just bags of chemicals, but intricate systems with sophisticated machinery. Cells communicate with neighbors through chemical signals. They sense and respond to their environment. They transport materials along microscopic tracks. They generate electrical signals. They move, change shape, and specialize into hundreds of different types in complex organisms. Stem cells, capable of differentiating into various cell types, have become crucial for research and medicine. Embryonic stem cells can become any cell type, offering potential for regenerating damaged tissues. Adult stem cells, with more limited differentiation potential, continuously renew tissues like blood and skin. Induced pluripotent stem cells, adult cells reprogrammed to an embryonic-like state, avoid ethical concerns about embryonic stem cells while offering similar potential. The cell theory demonstrates how technological advances enable scientific progress. Better microscopes revealed cellular structure. Staining techniques made internal features visible. Electron microscopy revealed subcellular details. Molecular techniques probe cellular mechanisms at molecular levels. Each advance deepens understanding of how life works at its most fundamental level, the level of the cell, that remarkable, self-contained unit of existence that forms the building blocks of all living things. Imagine undergoing surgery fully conscious, feeling every cut, every stitch, experiencing agony so extreme that patients had to be physically restrained. For all of human history, this was reality. Surgery was brutal, quick. Speed was essential to minimize suffering, and often fatal. Patients died from shock as often as from infections. The discovery and development of anesthesia, drugs that eliminate pain and consciousness during medical procedures, represents one of medicine's greatest humanitarian advances, transforming surgery from desperate last resort to routine intervention. Pain relief during surgery was desperately sought for centuries. Alcohol, opium, and various herbs provided partial relief but couldn't eliminate pain during major operations. Some surgeons tried compressing blood vessels to limbs, hoping reduced blood flow would decrease sensation. Others tried ice to numb tissue. Nothing worked adequately. The breakthrough came in the 1840s with several substances. Nitrous oxide, laughing gas. Discovered by Joseph Priestley in 1772, was noted to have pain-reducing and consciousness-altering effects. Horace Wells, a dentist, tried using it for tooth extractions in 1844 with limited success. His demonstration failed when the patient cried out, ending Wells's pursuit of the technique, though later investigations suggested the patient felt pressure without pain. William Morton, another dentist, experimented with ether. On October 16, 1846, at Massachusetts General Hospital in Boston, he publicly demonstrated ether anesthesia during surgical removal of a tumor. The patient remained unconscious and didn't react to the surgeon's cuts. When the operation concluded successfully, the surgeon famously said, "Gentlemen, this is no humbug." News spread rapidly, and within months ether anesthesia was being used worldwide. Chloroform, introduced shortly after by James Simpson in Scotland, became popular because it was more pleasant-smelling than ether and required smaller doses. Queen Victoria's use of chloroform during childbirth in 1853 lent its social acceptance despite religious objections that pain in childbirth was divinely ordained. Anesthesia revolutionized surgery. Operations previously too painful or shocking to attempt became feasible. Surgeons could work carefully and precisely rather than racing against time and patient endurance. Complex procedures requiring hours became possible. Survival rates improved as surgeons worked under better conditions. However, early anesthetics had risks. Dosing was imprecise. Too little left patients conscious. Too much stopped breathing or heartbeat. Different patients metabolized drugs differently. Chloroform could cause fatal liver damage. Ether was flammable and explosive. Deaths from anesthesia, while rare, occurred and spurred development of safer techniques and monitoring equipment. Modern anesthesia has become remarkably sophisticated. Anesthesiologists use combinations of drugs, some inducing unconsciousness, others preventing pain, others relaxing muscles. Continuous monitoring of heart rate, blood pressure, oxygen levels, and brain activity ensures patient safety. Precisely controlled ventilators maintain breathing while patients are paralyzed. Recovery is predictable, with patients typically waking shortly after drugs are stopped. Different types of anesthesia suit different procedures. General anesthesia produces complete unconsciousness for major surgery. Regional anesthesia blocks sensation in body parts, epidurals for childbirth, spinal blocks for leg surgery. Local anesthesia numbs small areas for minor procedures. Sedation provides relaxation and memory loss without complete unconsciousness. The development of anesthesia required courage from both pioneers and patients. Early subjects faced unknown risks trying untested drugs. Credibility battles ensued. Multiple people claimed priority for discovering anesthesia, leading to bitter disputes. But the humanitarian benefit was so obvious that adoption proceeded rapidly despite controversies. Anesthesia's introduction paralleled antiseptic techniques, and together they transformed surgery from dangerous ordeal to safe, routine medical intervention. Life expectancy increased as operations that would have killed patients through shock and pain became survivable. Quality of life improved as painful conditions could be corrected surgically. Dentistry became tolerable, encouraging people to seek necessary treatment. Today we take anesthesia for granted, assuming medical procedures will be pain-free. This wasn't always the case, and billions of people throughout history suffered needlessly. The discovery of anesthesia represents not just scientific advance, but profound humanitarianism. The application of chemical knowledge to reduce suffering, demonstrating how science in service of compassion can transform the human experience for the better. Light seems instantaneous. Flip a switch and the room illuminates immediately. For centuries, whether light traveled infinitely fast or had finite speed was debated. Establishing that light has a specific, finite speed, approximately 300,000 kilometers per second in vacuum, proved crucial for understanding light's nature and became foundational for physics, particularly special relativity. Galileo attempted to measure light's speed in the early 17th century through a simple experiment. Two people with lanterns on distant hills, uncovering and covering them in sequence. If light traveled slowly enough, a delay should be detectable. No delay was observed, but this was inconclusive. Perhaps light was just too fast for the method to measure. Ole Romer made the first successful measurement in 1676 through astronomical observation. He was timing eclipses of Io, Jupiter's moon, as it passed behind Jupiter. He noticed that eclipses occurred earlier when Earth was approaching Jupiter in its orbit and later when Earth was receding. This made sense if light took time to cross the changing distance between Earth and Jupiter. From the timing differences and known orbital distances, Romer calculated light's speed as about 220,000 kilometers per second. Not entirely accurate, but correct in showing light has finite speed. James Bradley refined measurements in 1728 through stellar aberration, the apparent displacement of star positions caused by Earth's orbital motion combined with light's finite speed. His calculations yielded about 300,000 kilometers per second, much closer to modern values. Laboratory measurements came in the 19th century. Hippolyte Fizeau used a rapidly rotating toothed wheel in 1849. Light passed through gaps between teeth, traveled several kilometers to a mirror, and returned. If the wheel rotated so teeth blocked returning light, he could calculate light's speed from the wheel's rotation rate and distance traveled. His result was remarkably accurate. Léon Foucault improved Fizeau's method in 1862, using rotating mirrors instead of toothed wheels, achieving greater precision. By the late 19th century, light speed was known to be approximately 299,800 kilometers per second in vacuum. Albert Michelson devoted much of his career to increasingly precise measurements. His most accurate experiments, conducted in the 1920s, established the value as 299,792.458 kilometers per second in vacuum, with a small margin of error. Modern measurements using lasers and atomic clocks have refined this further, and since 1983, the speed of light has been fixed by definition at exactly 299,792.458 kilometers per second, with the meter now defined in terms of this fixed light speed. Why does light speed matter so profoundly? First, it's remarkably constant. Light travels at the same speed in vacuum regardless of observer motion or light source motion. This constancy seemed strange before relativity theory explained it. Second, it's a cosmic speed limit. Nothing with mass can reach light speed, and information cannot propagate faster than light. Third, it connects space and time through relativity, with the speed of light appearing in Einstein's most famous equation, E equals mc squared. Light's finite speed has practical implications. We see the sun as it was 8 minutes ago because light takes that long to reach Earth. We see the nearest star, Proxima Centauri, as it was 4.2 years ago. Distant galaxies appear as they were billions of years ago. Telescopes are time machines looking into the past. Astronomical distances are measured in light years. The distance light travels in 1 year, about 9.5 trillion kilometers. Communication with space probes faces light speed delays. Messages to Mars take between 4 and 24 minutes one way depending on planetary positions. Commands to Voyager 1, over 20 light hours away, take over 20 hours to arrive, with responses taking another 20 hours to return. This constrains how missions operate. Distant spacecraft need autonomous capabilities because real-time control is impossible. The constancy of light speed proved crucial for relativity theory. Einstein's special relativity rests on two postulates. Physical laws are the same in all inertial reference frames, and light speed in vacuum is constant for all observers regardless of their motion or the light source's motion. These seemingly simple principles lead to profound consequences: time dilation, length contraction, relativity of simultaneity, and mass-energy equivalence. Understanding light speed also revealed light's electromagnetic nature. Maxwell's equations predicted electromagnetic waves traveling at a specific speed determined by electric and magnetic constants. Calculation yielded the observed speed of light, suggesting light consists of electromagnetic waves, a prediction confirmed when Heinrich Hertz generated and detected radio waves. Measuring light's speed represents science at its best. Careful observation, ingenious experimental design, progressive refinement, and recognition that seemingly esoteric measurements can have profound theoretical significance. The speed of light isn't just a number. It's woven into the universe's fundamental structure, constraining how events connect, how information propagates, and how space and time relate to each other. As you continue to relax, let the remaining discoveries wash over you like gentle waves. The electromagnetic spectrum revealed that visible light represents only a tiny fraction of electromagnetic radiation. Radio waves let us communicate wirelessly, microwaves cook our food, infrared warms us, ultraviolet tans skin, X-rays peer through flesh, and gamma rays emerge from nuclear reactions. Each wavelength a window into different aspects of reality. Radioactivity showed that atoms themselves can transform, discovered by Henri Becquerel and explored by Marie and Pierre Curie. Unstable atomic nuclei emit particles and energy, eventually transforming into different elements. This natural alchemy opened doors to nuclear energy, medical treatments, and understanding stellar processes where heavy elements form. The electron, discovered by J.J. Thomson, revealed that atoms contain even smaller particles. These tiny charged particles orbiting atomic nuclei determine all chemical properties, conduct electricity, and enable the entire electronic age that surrounds us. Quantum theory emerged from Max Planck's study of blackbody radiation, showing energy comes in discrete packets called quanta. This seemingly technical finding revolutionized physics, revealing that at microscopic scales, nature behaves in ways completely unlike everyday experience. Probabilistic, uncertain, and wonderfully strange. Special relativity showed that space and time interweave, that simultaneity is relative, that moving clocks run slower and moving objects contract in length. Einstein's famous equation E equals mc squared showed mass and energy are equivalent, explaining both why the sun shines and why atomic weapons release such terrible power. General relativity described gravity not as a force, but as space-time curvature caused by mass and energy. Massive objects warp the fabric of space and time itself, and this curvature guides how objects move, how light bends, how time passes differently in different gravitational fields. X-rays, discovered accidentally by Wilhelm Röntgen, allowed seeing through opaque materials for the first time. Medical diagnosis transformed as doctors could examine bones and internal organs without surgery. X-ray crystallography later revealed molecular structures, including DNA's famous double helix. Vitamins emerged from recognizing that food contains not just calories, proteins, fats, and carbohydrates, but tiny quantities of essential substances preventing specific diseases. Scurvy, beriberi, rickets, and pellagra, each caused by vitamin deficiency, each preventable through proper nutrition. Insulin's discovery and purification by Banting and Best transformed diabetes from a death sentence into a manageable condition. Millions of people worldwide live normal lives because injecting this hormone regulates blood sugar that their bodies cannot control naturally. Antibiotics, beginning with penicillin discovered by Alexander Fleming, brought humanity's first truly effective weapons against bacterial infections. Diseases that killed millions, pneumonia, tuberculosis, wound infections, became treatable. Though bacterial resistance now threatens antibiotic effectiveness, These drugs have saved countless lives. Blood types, identified by Carl Landsteiner, explained why transfusions sometimes killed patients. Compatible types can mix safely. Incompatible types cause fatal reactions. Blood banking became possible, saving trauma victims and enabling complex surgeries. Vaccination, pioneered by Edward Jenner and refined by many others, trains immune systems to recognize and fight pathogens before encountering them naturally. Smallpox has been eradicated, polio nearly eliminated, and numerous diseases prevented through systematic vaccination programs. The structure of DNA, elucidated by Watson and Crick building on Franklin's X-ray crystallography, revealed how genetic information stores, copies, and transmits across generations. The elegant double helix with complementary base pairing explained heredity's molecular mechanism. Plate tectonics unified geology by showing that Earth's surface consists of moving plates, explaining earthquakes, volcanoes, mountain formation, and continental drift. The theory revealed our planet as dynamic and ever-changing rather than static and eternal. The uncertainty principle, formulated by Heisenberg, showed fundamental limits to knowing both position and momentum of particles simultaneously. This isn't measurement limitation, but reflects reality's intrinsic nature. At quantum scales, certain properties simply don't have definite values until measured. Wave-particle duality revealed that light and matter exhibit both wave and particle properties depending on how they're observed. Electrons create interference patterns like waves, but arrive at detectors as discrete particles, challenging intuitive notions about reality's fundamental nature. Quantum mechanics matured into a complete mathematical framework describing atomic and subatomic behavior. Despite its counterintuitive implications, quantum mechanics is physics' most precisely tested theory, predicting phenomena with astonishing accuracy and enabling technologies from lasers to computer chips. Nuclear fission, discovered when uranium nuclei split after absorbing neutrons, releases enormous energy from atomic nuclei. This discovery enabled both devastating weapons and powerful electricity generation, demonstrating science's double-edged nature as tool for either destruction or construction. Nuclear fusion, the process powering stars where light nuclei combine into heavier ones, releases even more energy than fission. Achieving controlled fusion on Earth remains challenging, but promises nearly limitless clean energy if technical hurdles can be overcome. The transistor revolutionized electronics by enabling compact, reliable amplification and switching of electronic signals. This tiny device made possible all modern computers, smartphones, and digital technology, transforming human civilization more rapidly than perhaps any other invention. Laser technology produces coherent, focused light with countless applications. Reading barcodes and optical discs, performing delicate surgeries, enabling fiber optic communication, cutting materials precisely, and making fundamental physics measurements. Integrated circuits place thousands, then millions, now billions of transistors on single chips, driving exponential growth in computational power while shrinking size and cost. This miniaturization underlies the entire digital revolution. The Big Bang Theory explains the universe's origin and evolution. All matter, energy, space, and time emerged from an incredibly hot, dense state approximately 13.8 billion years ago, expanding and cooling ever since. Evidence includes cosmic microwave background radiation and element abundances matching predictions. Cosmic microwave background radiation, discovered accidentally by Penzias and Wilson, represents light from when the universe became transparent roughly 380,000 years after the Big Bang. This fossil radiation provides a snapshot of the early universe's conditions. Pulsars, discovered by Jocelyn Bell Burnell, are rapidly spinning neutron stars emitting beams of radiation like lighthouses. These extreme objects, with masses exceeding our Sun compressed into spheres barely 15 kilometers across, test physics under conditions impossible to recreate on Earth. Black holes, predicted by general relativity and now observed throughout the universe, are regions where space-time curvature becomes so extreme that nothing, not even light, can escape. They represent the ultimate gravitational extremes, where our understanding of physics breaks down at central singularities. Dark matter, making up about 27% of the universe's mass energy, reveals itself only through gravitational effects. Galaxies rotate too fast for their visible matter alone. Something invisible but massive must be present. Its nature remains one of physics' greatest mysteries. Exoplanets, planets orbiting other stars, number in thousands and likely trillions throughout our galaxy. Many orbit in habitable zones where liquid water could exist. The discovery that planets are common raises fascinating questions about life's prevalence in the universe. Gravitational waves, detected directly in 2015, are ripples in space-time itself caused by accelerating massive objects like merging black holes. Their detection confirmed general relativity's last major prediction and opened a new window for observing the universe. The accelerating universe's discovery showed that cosmic expansion is speeding up rather than slowing down as expected. Something dubbed dark energy apparently makes up about 68% of the universe's mass energy, counteracting gravity and driving accelerating expansion. The genetic code, cracked by numerous scientists, revealed how DNA triplets specify amino acids and proteins. This universal code, shared by all life on Earth, provides strong evidence for common ancestry and enabled biotechnology revolution. DNA sequencing technology allowed reading genetic information, progressing from laborious manual methods to rapid automated techniques. This enabled the Human Genome Project and now allows sequencing individual genomes affordably, revolutionizing medicine and biological research. Genetic engineering enabled directly modifying organisms' DNA, creating organisms with desired traits. Applications range from insulin-producing bacteria to pest-resistant crops to experimental gene therapies potentially curing genetic diseases. PCR, polymerase chain reaction, allows copying specific DNA sequences millions of times from tiny samples. This revolutionary technique enabled DNA fingerprinting, ancient DNA analysis, disease diagnosis, and countless research applications. The Human Genome Project sequenced all 3 billion DNA base pairs in human chromosomes, creating a reference genome and catalyzing genomics explosion. Understanding which genes do what continues, but having the complete sequence was a crucial milestone. CRISPR gene editing technology allows precise, relatively easy modification of DNA in living organisms. This powerful tool promises treatments for genetic diseases, improved crops, and research capabilities previously unimaginable. though ethical concerns about human genetic modification remain unresolved. Stem cells, capable of differentiating into various cell types, offer potential for regenerating damaged tissues and treating degenerative diseases. Research continues to harness their therapeutic potential while navigating ethical considerations. Epigenetics revealed that gene activity can be modified without changing DNA sequence itself. Chemical tags can turn genes on or off, influenced by environmental factors and potentially inherited across generations. This adds complexity to understanding how genes and environment interact. Computer programming languages evolved from direct machine code to high-level languages, allowing humans to instruct computers efficiently. Software became as important as hardware, enabling computers to perform vast ranges of tasks through different programs. The Internet connected computers globally into a vast network, enabling information sharing and communication at unprecedented scale. Originally developed for military and academic purposes, it transformed into the backbone of modern civilization. The World Wide Web, created by Tim Berners-Lee, made the Internet accessible to ordinary people through browsers, hyperlinks, and web pages. Information became readily available to anyone with connectivity, democratizing knowledge like nothing before. Artificial intelligence progresses toward machines performing tasks requiring human-like intelligence, recognizing images and speech, translating languages, playing games, driving vehicles, diagnosing diseases. Whether machines can truly think or just simulate thinking remains philosophically debated. Quantum computing harnesses quantum phenomena like superposition and entanglement for computation, potentially solving certain problems exponentially faster than classical computers. Though still in early stages, quantum computers might revolutionize cryptography, drug discovery, and optimization problems. Fiber optics transmit information as light pulses through glass strands thinner than human hairs, enabling high-speed data transmission over long distances with minimal loss. Modern internet infrastructure relies heavily on fiber optic cables spanning continents and oceans. GPS, Global Positioning System, uses satellites and relativistic corrections to enable precise position determination anywhere on Earth. Applications range from navigation to synchronizing networks to tracking everything from wildlife to delivery packages. MRI, magnetic resonance imaging, uses powerful magnets and radio waves to create detailed images of soft tissues inside bodies without radiation or surgery. This non-invasive technique revolutionized medical diagnosis and neurological research. The Higgs boson, discovered at CERN in 2012, confirmed the Higgs field permeating all space and giving particles their mass. Finding this long-predicted particle validated the standard model of particle physics and represented a triumph of experimental and theoretical physics. Graphene, a single layer of carbon atoms arranged in hexagonal lattice, exhibits remarkable properties: stronger than steel, more conductive than copper, nearly transparent, extremely flexible. Potential applications span electronics, materials science, energy storage, and water purification. Climate change science revealed that human activities, particularly fossil fuel burning and deforestation, increase atmospheric greenhouse gases, warming the planet with consequences including rising seas, changing weather patterns, ecosystem disruptions, and threats to human societies. Immunotherapy harnesses the body's immune system to fight cancer. Teaching immune cells to recognize and attack cancer cells has produced remarkable successes in previously untreatable cancers, though it doesn't work for all cancer types or patients. Renewable energy technologies, solar panels converting sunlight to electricity, wind turbines extracting energy from moving air, energy storage systems, advance toward replacing fossil fuels with sustainable energy sources, crucial for addressing climate change. And so, as we reach the end of our journey through humanity's greatest discoveries, let yourself settle even deeper into comfort. These 77 moments of understanding represent our species' long journey from confusion to clarity, from powerlessness to capability, from ignorance to wisdom. Each discovery built upon those before it, each generation standing on the shoulders of giants who preceded them, slowly constructing an ever more complete picture of reality. You don't need to remember every detail we've explored tonight. Let them blur together. Let them fade like stars at dawn. Let them become simply a background murmur of human achievement accompanying you into sleep. What matters isn't memorizing facts, but appreciating the broader story, that we are a species capable of understanding, of questioning, of discovering truth through patience and persistence. Sleep now, knowing that the universe we inhabit, while vast and sometimes incomprehensible, follows patterns we can discern and laws we can discover. Rest assured that human curiosity continues, that tonight as you sleep, researchers somewhere are making new observations, testing new hypotheses, pushing the boundaries of knowledge a little further. Tomorrow's discoveries will build on today's understanding, and the journey continues. If you enjoyed this exploration of scientific discovery, please like this video and subscribe to the Sleeping Subconscious for more content that blends education with relaxation. Sweet dreams, and may your sleep be as peaceful as the constants that govern our universe, as deep as the ocean trenches we've explored, as refreshing as the understanding that comes when mystery yields to knowledge. Good night.